IBM's new Lightspeed processor shocks the entire industry. To quench computers' virtually unlimited thirst for processing power, IBM researchers have unveiled a new approach that could have far-reaching impacts for computer applications, a processor that performs computations entirely with light rather than electricity, which means it could perform 1,000 trillion multiply accumulate operations per second. But how fast is it in comparison to a standard silicon-based processor? Buckle up because this is going to be a very fast ride. Let's get started right away. Did you know that beach sand is used as a raw material in a $500 billion industry? This massive industry is known as the semiconductor industry. If you're unfamiliar with the term semiconductor, perhaps you're familiar with the term transistor. If not, you must be aware of what a CPU is. The transistor is the greatest invention of the 20th century, and it's both simple and highly complex. Let's begin with the simple part. A transistor is a small electronic component that can perform two functions. It can function as an amplifier or a switch. The most basic application of the transistor is as a switch. The simple mode of switching underpins the entire ultra-complex computer. The transistor is widely used for switching operations, such as opening or closing a circuit. Meanwhile, the fundamental concept underlying the operation of a transistor as a switch is dependent on its mode of operation. In this mode, transistors generally turn on or off the low-voltage DC by bypassing both bipolar transistors with a on-off static switch. When used as an amplifier, it accepts a small electric current at one end and produces a much larger electric current at the other. In other words, it acts as a current booster. This is extremely useful in applications such as hearing aids, which were among the first applications for transistors. A hearing aid contains a tiny microphone that picks up sound from the environment and converts them into oscillating electric currents. These are routed through a transistor, which amplifies them and powers a very tiny loudspeaker, allowing you to hear much louder versions of the sounds around you. Engineers realized that transistors would replace vacuum tubes in computers once mass-produced transistorized hearing aids became a reality. The famous ENIAC electronic numerical integrator and computer, one of the first pre-transistor computers, weighed 30 tons, thanks in part to its more than 17,000 vacuum tubes. It was self-evident that transistors would fundamentally alter computer engineering and result in smaller and better machines. Although germanium transistors aided in the beginning of the computer age, silicon transistors revolutionized computer design and spawned an entire industry in California's appropriately named Silicon Valley. George Teal, a scientist at Texas Instruments, invented the first silicon transistor in 1954. Manufacturers quickly developed methods for mass-producing silicon transistors, which were less expensive and more reliable than germanium-based transistors. Silicon transistors played great in computer manufacturing. With clever engineering, transistors enabled computers to perform massive amounts of computation in a short period of time. Transistors' simple switch operation is what allows your computer to perform massively complex tasks. Transistors in a computer chip alternate between two binary states, 0 and 1. This is the computer language. Millions of transistors on a single computer chip can be switched continuously, assisting in the completion of complex calculations. The transistors in a computer chip are not isolated individual components, they're actually a component of an integrated circuit, also known as a microchip, in which many transistors collaborate to help the computer complete calculations. An integrated circuit is made up of a single piece of semiconductor material that contains transistors and other electronic components. Computers make simple decisions by combining these currents with Boolean algebra. A computer with several transistors can make many simple decisions quickly and thus perform complex calculations quickly. To complete tasks, computers require millions, if not billions, of transistors. Engineers can pack an unimaginable number of transistors into a wide range of computer and computer-related products due to the dependability of incredibly small size of individual transistors, which are much less than the diameter of a single human hair. The electronics industry has been driven by Moore's law for the last 4 decades, which states that the number of transistors incorporated into a chip will approximately double every 24 months. Transistors, which are tiny electrical switches, are the fundamental unit that powers all electronic devices. They become faster and consume less electricity as they become smaller. One of the most challenging technological questions of the 21st century is, how small can we make transistors? If there's a limit to how small they can become, we may reach a point to where we can no longer make smaller, more powerful, and more efficient devices. Because transistors are made of atoms, no transistor can be smaller than a single atom. Companies like Intel are currently mass-producing transistors 14 nanometers across, only 14 times wider than DNA molecules. They're made of silicon, our planet's second most abundant material. The atomic size of silicon is approximately 0.2 nanometers. Because today's transistors are approximately 70 silicon atoms wide, the potential of making them even smaller is diminishing. We're getting close to the limit of how small a transistor can be. It's because of both physics and technology. Physics states what is theoretically possible, and engineering brings technology as close to these theoretical limits as is practically possible. When you get down to the subatomic level, charged particles begin to behave like waves. This is what imposes the limit. When the width of the gate oxide is thinner than the wave function of the electrons flowing past it, it ceases to be a switch and begins to conduct as electrons tunnel through. This becomes a problem at 5 nanometers. As a result, 3D designs such as introducing and manipulating strain with a mix of silicon and germanium will be used to create shorter effective gate lengths or higher transistor density, possibly approaching 0.5 nanometers. These two were previously proportional, but this stopped somewhere between 90 nanometers and 25 nanometers, depending on the process. For over a decade, the frequency of ambient minimum CPUs has remained constant around 5 GHz. So we've already reached our limit. This is where IBM's optical processors come into play. Currently, transistors communicate by sending electrical signals, electrons moving from one location to another. However, light-based processors use light, made up of photons, rather than electricity, making transistors even faster. Okay, we'll try to make it a little easier for you. Consider transistors to be 3 parts of a digital camera. First, information enters the lens, analogous to the source of a transistor. The signal is then routed through a channel from the image sensor to the camera's wires. Finally, the data is saved on the computer's memory card, which is known as a transistor's drain, where the data eventually ends up. All of this is currently accomplished by moving electrons around. IBM is using photons to replace light as the medium. Subatomic particles such as electrons and photons move in a wave motion, vibrating up and down while moving in one direction. The length of each wave is determined by the medium through which it travels. The most efficient wavelength for photons in silicon is 1.3 micrometers. This is extremely small. A human hair is about 100 micrometers wide. However, electrons in silicon have wavelengths that are 50 to 1,000 times shorter than photons. This means that photon handling equipment must be larger than electron handling devices currently in use. As a result, it may appear that it would force us to build larger transistors rather than smaller ones. However, IBM keeps chips the same size while providing more processing power, as they shrink chips while providing the same power or both. To begin, a photonic chip requires only a few light sources to generate photons, which are then directed around the chip using a very small lens and mirrors. Second, light travels much faster than electrons. Photons can travel roughly 20 times faster than electrons in a chip. That translates to computers that are 20 times faster, a speed increase that would take about 15 years with current technology. Although this IBM processor has only been tested on a small scale, the study says that as the processor evolves, it could achieve 1,000 trillion multiply accumulate operations per second and per square millimeter, 2 to 3 orders of magnitude more than the state-of-the-art AI processors that rely on electrical signals. That pretty much wraps up this video, guys. What are your thoughts on this light-based processor, and when do you think that it will be available to the public? Let us know in the comments below. Thanks for watching. Remember, and make sure to subscribe to this channel with bell notifications on if you enjoy our content. We upload some pretty awesome stuff here, which you'll certainly enjoy. So hit a like on the video, leave a comment below, and we'll see you guys in the next one.